Gyroscopes have usually been presented as really difficult to understand intuitively. The explanations are usually couched in terms of vector mathematics. This video will try to give you a way to understand the reasons gyroscopes do what they do without vectors or equations. To understand gyroscopes intuitively, you don't really need any maths. You do need to understand momentum, but that's pretty basic. Everybody intuitively understands momentum. It's what keeps vehicles going when you take your foot off the gas. It's a quality that tennis balls and ice hockey pucks and every other moving object possesses. There's some explanation of angular momentum at the end of the video, but by then, to you, gyroscopes will have lost the mystique they have had for centuries. One amazing thing about gyroscopes is that Newton first described the laws that govern them 300 years ago, and still they confuse us. Even today, people are still writing patents about inventions they have created with gyroscopes, and people also frequently write to NASA about an anti-gravity machine they have invented based on gyroscopes. So let's take a quick look at Newton. On this chart, almost every entry could be the subject of a thick book. There were 7 changes of royalty and government. One king had his head chopped off. Another escaped to France. A Dutch king was invited to take over the English throne. Throughout this period there was a conflict going on between the kings, the religious authorities, and Parliament. The kings thought they should be able to rule divinely. They also supported either the Protestant or Catholic religions of the time. Parliament, on the other hand, wanted the country to be Protestant, with laws decided by them and not the kings. While this was going on, there was a great plague in London, and a year later a great fire in London that destroyed most of the city. In the New World of America, Boston was becoming a commercial centre, and New Orleans was just being founded. Newton seemed to go through these turbulent times mostly unaffected. By the time he was 26, he was a professor of maths at Cambridge. Then he was made a member of Parliament. He was knighted, becoming Sir Isaac Newton, and then he was made Master of the Royal Mint, where, as well as his administrative duties, he was responsible for executing counterfeiters. Sir Isaac Newton, MP, FRS, lived to be 84 years old. In those days, that was very old indeed. The average lifespan of even royals was only 54 years. These are Newton's 3 laws of motion. You only need to remember and understand the first one. Things move in a straight line unless some force acts on them. To continue our analogy, a vehicle encountering an icy patch on the road goes in a straight line. If you take away all other forces such as air resistance, friction, gravity or mechanical constraint, everything would travel in a straight line at the same speed, in the same direction, forever. To understand why gyroscopes are confusing, let's hear the introduction to an American college physics course on gyroscopes.
We now come to the most non-intuitive part of all of 801, and arguably perhaps the most difficult part in all of physics, and that has to do with gyroscopes. And I really urge you to pay a lot of attention and not even to miss 10 seconds, because you're going to see some mind-boggling demonstrations which are so incredibly non-intuitive that unless you have followed the steps that lead up to it, you won't have any idea what you're looking at. It will be fun, it will be cute, but it won't do anything for you.
Okay, that was scary. Now let's listen to a famous UK professor and engineer talking in the 1970s.
So really precesses, then we've made one in which the rim has been subdivided into a lot of little masses on spring wires, so that when I set it in motion, turn it to the camera, you can see this. If I now waggle it side to side, the inner ring that is, you can see the precession taking place, not about the point you thought, not about the midpoint here, but about the top and bottom. And if I give the inner ring a spin, you can see this leaning over like a dinner plate. Can you see that? Incidentally, I said that when you had a gyro going, it wanted to maintain its axis of spin. Why isn't that stopping the minute I let go? It wasn't what the other gyros did. There's one for you to think about. I'll answer that next time. Thank you.
Professor Lathwaite, who you've just seen, didn't accept that gyroscopes obeyed Newton's laws of motion for decades. He even set up a company to take advantage of what he thought of as a method of propulsion that broke Newton's third law. He's only one of thousands of people who thought that. The difference was that he was a professor and should have known better, but the way gyroscopes work was a bit of a blind spot for him. Pause the slide if you want to read more about it, but this is the patent Professor Lathwaite produced based on gyroscopic motion. It illustrates why gyroscopes are confusing at first. There are new words to learn, and the motion involves multiple things moving in many directions at the same time. It makes it difficult to describe what is happening in simple terms. Sometimes scientists can make mistakes which confuse people even more. The authors of this paper thought they had discovered anti-gravity and managed to get their paper published. No other scientific group was able to duplicate their results, so they eventually drowned in ignominy. But it goes to show how few people were confident enough to immediately call foul on their results, which were probably the result of confirmational bias. Nowadays, NASA gets so many letters about new gyroscopic inventions, it has published a helpful guide for any would-be inventors. Before submitting anything, inventors are asked to make sure their inventions pass certain tests. If the inventions do pass the tests, NASA would certainly be interested in hearing about them. Today, patents are still produced that purport to produce an anti-gravity or a miraculous thrust engine, and the Patents Office still collects fees for registering the ideas. Some of the ideas might use new quantum physics ideas that will open up new possibilities for space travel. Other ideas may use words plucked from the latest developments in physics, but are no more than camouflage for a naive concept or an attempt to access grant monies. Very few people are capable of reading the best of these ideas and saying immediately, "That sounds like it might work," or "That's rubbish, it'll never work." Okay, after that background, we're now going to try and understand how gyroscopes work. And to do that, we're going to use the following graphic, which splits the rim of the gyroscope into a small number of very heavy arrow-shaped pieces, attached to the hub by spokes that can bend a small amount. This image of a gyroscope with the rim split into separate pieces is the one to keep in mind every time you look at a gyroscope. It behaves exactly the same as a gyroscope with a solid rim, like a weighted bicycle tire, but focusing on the momentum of the pieces and the forces on the spokes will allow you to predict what will happen. Now let's see what happens in real life.
I hold it in my hand, I spin it towards you, and I'm going to put my right hand towards you and my left hand away from you. The spin angular momentum is now in this direction. So I'm going to give it a torque like so, that means up, and what will the wheel do? The wheel will do this. It's very non-intuitive. Watch it. Isn't that strange? You wouldn't expect that. I'll do it again. So I'm going to torque by pushing my hand towards you. And the wheel does something completely unexpected. It simply tilts. If I torque the other way around, then the torque, of course, will make it flip like this. I'll give it a little bit more spin angular momentum. So now I move my left hand towards you and my right hand towards me, and then I expect that the wheel will do this. And that's what it does. Extremely non-intuitive.
This graphic represents what you've just seen in real life. As the axle is twisted, it seems to have a life of its own and tries to turn in a different direction, ending up twisted in both the horizontal and the vertical plane. Picture 1 is looking at the gyroscope from the viewpoint of the person holding the axle. Pictures 2 and 3 are views looking down on top of the gyroscope before and after the axle is twisted in the horizontal plane. The green arrows are forced out of their original motion by the effort of the person holding the axle, but the red arrows want to keep moving in the direction of their original motion. Now imagine that the red arrow was hollow and contained a lot of lead shot. As the axle was twisted, all the lead shot would crowd into the right-hand side of the hollow arrow and try to continue in their original direction. They would act like a force on the right-hand side of the red arrow and try to bend the spoke holding the arrow to the right. That spoke in turn would act as a lever on the hub of the axle, bending it upwards. In diagram 6 the effect has been exaggerated. The spokes don't visibly bend, but the force is still acting to twist the axle. This is just a closer picture of what's happening at the axle. The red arrows try to continue in their original direction, and this bends the spokes, which transmit the force to the hub, twisting it around the y-axis. That's really all there is to it. Just by considering the conservation of momentum and the stresses on the spokes of the gyroscope, all its strange behavior can be explained. Now let's look at precession, which is what happens when one end of the axle is supported and the other end is left to move freely.
Angular momentum is now in this direction. See, it's turning the other way around. Angular momentum is in this direction. Torque is now towards me. Angular momentum is changing the torque. I've changed the direction of the spin angular momentum. I've not changed the direction of the torque, and now it is rotating, as seen from below, counterclockwise. Before it was rotating clockwise.
In the many explanations of gyroscopic motion over the years, what was missed for a long time is that the gyroscope has to fall, just a little, to begin the precession. From diagram 10 we can see why. This time the red arrows are forced into a new path by gravity, and they try to resist this. If the momentum is high enough, they can resist gravity and force end A of the long axle to support their weight. If there was a weighing machine attached to the string at A, it would measure the full weight of the gyroscope. However, the green arrows haven't been forced into a new trajectory. Looking down in the Z direction, we can see that the green arrows still want to continue on their original path. This bends the spokes slightly in the XY plane, and the stresses on the spokes produce a torque on the axle which causes the gyroscope to precess in the anti-clockwise direction, looking down. If the gyroscope was spinning in the opposite direction, it would precess in the clockwise direction. Now let's consider the situation where the person holding the gyroscope is sitting in a revolving chair.
I'm going to torque exactly as you see on the picture there. You ready? I stop the torque. Nothing happens. I torque backwards. I keep torquing. I keep torquing. I feel it in my hand. I really have to push. I keep torquing. And I stop torquing and it stops. So the angular momentum vector is chasing, so to speak, the torque. Is that non-intuitive? Very non-intuitive?
Once you start looking at the direction in which the arrows want to continue and the stresses on the spokes, the motion becomes understandable. Looking along the y direction, if the axle ends A and B are forced down and up respectively, then the gyroscope will want to twist towards and away from the person. But the person's arms don't get longer and shorter. They resist the twisting, and so the torque gets transferred to the person's body and then to the chair. Gyroscopic effects are only visible when the weight and the speed of the rim is considerable compared to the other forces acting on the gyroscope. That's because the gyroscope needs a lot of momentum to resist the changes forced on it by the person holding the gyroscope or by gravity. Now we'll take a look at angular momentum, because that's usually the way gyroscopes are explained. Angular momentum is just a construct to make certain situations easier to work out. Angular momentum is really just regular momentum, but usually defined when something is moving in a circular path. However, a football traveling in a straight line between 3 catchers has angular momentum relative to each of the catchers. It's different for each of them because it's a product of the football's mass, its velocity, and the distance of its nearest approach to that particular catcher. So we don't talk about the football just having angular momentum, but always about having angular momentum around a particular object. It'll have a different number and perhaps even a different sign for each of the catchers. Angular momentum is defined as being positive in the direction of the thumb if the fingers of the right hand curve in the direction of motion of the orbiting object. In the case of catchers A and C, that is the case, and the angular momentum is positive and coming out of the screen. In the case of catcher B, the angular momentum is negative and points into the screen. Considering diagram 1 again, and representing the person twisting the axle around Z as providing an angular momentum of dl, a really small change in angular momentum, we can add dl to the original angular momentum, which we can call L, to get to the final total momentum. When we add dl to L to get to the total angular momentum, it shows us the axle will have to twist around the y-axis as well as around the z-axis, exactly as it does in real life. I hope this has been useful in demonstrating that you can understand a gyroscope's motion intuitively, just by considering momentum and the forces acting on the axle of the gyroscope. The same understanding can be used to understand the precession of the Earth and the tilt of a bicycle. If you want to do some experiments of your own, this would be a good gyroscope to get. It's very heavy and it has a small motor that spins the gyroscope up to a high speed. This gives you a lot of time to observe its motion. NASA is waiting. Good luck.